Welcome to Flink Forward Asia 2024.
For this afternoon with the presentations about how we built a scalable, cost-effective cloud-native streaming platform in Lalamove. Altogether, Mrs. Jenny Chen and also Mr. Owen Ip, big data engineer and also from Lalamove. Please give a round of applause for Mrs. Jenny Chen and Mr. Owen Ip.
Testing. Good afternoon, everyone. I'm Owen Yip. Good afternoon, everyone. I'm Owen Yip. I'm a data engineer from Lalamove. I'm happy to be here to share how we build a scalable, cost-effective, cloud-native streaming platform in our company. And I will co-presenting today's material with my colleague, Jenny Chen. She's also a senior data engineer in Lalamove. So here's today's outline. We will starting from the introduction to our company and the overview of our streaming platform. Then we will delve into the challenge we face while building our cloud-native platform. And finally, we will share our experience using Apache Paimon to enhance the stability of our existing data pipeline. So let's begin. So Lalamove is a 24/7 on-demand delivery service platform. Our service covers 30 markets with over 400 cities globally, spanning Asia, Latin America, and EMEA. And Lalamove was born with mission to empower our local communities to making the delivery service faster, simple, and affordable. And individuals, small business, the corporation can access wider fleets of delivery vehicle with our professional driver partners. And Lalamove now achieved the world's largest logistic transaction platform in the first half of the year, and with 1.4 million monthly active driver and over 15 million monthly active user. And these are just brief our company. Now let's talk about our streaming platform. Our platform are maintaining over 500 computing nodes with over 8,000 vcores at the peak season. And we deploy, manage 1,000 of streaming jobs on 2 regional clusters. And the user on our platform are typically used for real-time data analytics, anti-fog monitoring, and some location-based services. And we leverage the Apache Flink engine to process a massive amount of data with second latency and file processing throughput. Here's the architecture of our platform. Starting from the bottom, we are building our streaming platform on top of hybrid cloud service provider, including AWS and Azure. And we can schedule our job into both Yarn cluster and the Kubernetes clusters. For the engine layer, we provide a customized Flink SQL, extend the various connector, and we manage stateful computation, and also we support deploying different versions of Flink to our clusters. And for the task development, our user can submit either SQL or Jar tasks. They can investigate their data pipeline with the data lineage, and they can also upload the user-defined function for their custom business logic. And they can also do stress testing to ensure their data pipeline handle the increasing workload while peak seasons. And for task operation, we offer monitoring, logging, and alerting mechanisms to ensure users' data pipeline are stable, observable, and cost-effective. So now let's move on to the next chapter. How we ensure the high stability and cost effectiveness in our platform. So first, why did we migrate to Kubernetes cluster? There's three major reasons. The better scalability to scale our infrastructure resources compared to traditional Yarn cluster. And it also offers a better stability to recover from node disaster, and also the better isolation to prevent the interfering between Flink jobs deploying on the same machine. So here is our Kubernetes cluster architecture. We basically use the open source Flink Kubernetes operator to manage the life cycle of our Flink job. And we implement some customized feature like metrics reporter and listener to report the job status and operator metrics back to our streaming platform in order to manage the job on the Kubernetes. You now have some basic overview of our streaming platform. We can now start to talk about the challenges we face while building our platform. So the first challenge is the increasing workload due to our business growth. Our business keeps expanding to more markets and cities, and more business lines are open, and more users are using our delivery service. So we need to have some scalable platform and it's maintainable. And the second challenge is the continuous changing of technology evolution, especially the Kubernetes version cycle. In order to get the better stability, we have to keep our cluster up to date in order to get support from the cloud service provider. And also, we are constantly improving our platform and the Flink engine. And we have some mechanism to rolling out update to this optimization to the running jobs, because we have managing thousands of tasks, so we have some mechanism to manage them. These factors are obvious increase the maintenance costs on our platform. And the third challenge is the waste of infrastructure costs. You can see from the graph on the left, our business, we observe some pattern of the actual resources usage on our clusters. The resources usage is low during the nighttime, and resources become high during the daytime due to our business nature. So what if we can dynamically allocate the resources based on this pattern, like the graph on the right? So these three challenges, increasing the infrastructure costs and the maintenance costs, it drives us to think of the solution, which is the Autopilot. And we basically use Flink job to implement our Autopilot based on the rich connector and extendable connector or the Apache Flink offer. And we can collect job-related metrics from various sources using the Kafka connector, MySQL connector, and HTTP connector. And we use the Flink as a rule engine to help us to operate the tasks on the clusters. For example, we can base on the consumer latency metrics of a job to consume the Kafka topic. When the metrics latency is too high, we can adjust the parallelism of that job in order to increase the consumer speed. So and also we when a operation when we need to execute a operations, it also have to within the operational window and the resources boundary in order to make sure every actions that the Autopilot operates under our control. And once the action is determined, it will signal our streaming platform to actually execute that actions. So we now can leverage this Autopilot to help us reduce the maintenance costs. For example, for the Kubernetes upgrade, we choose to use blue-green upgrade strategy rather than in place. Then we can use the Autopilot and to set some auto migration rule to migrate the task on the old cluster to the new one. And the Autopilot can automatically migrate this job during the operational window to ensure it won't affect the production. For other kinds of operations, like the normal frame jobs handling, our Autopilot can keep monitoring the metrics. When it detects some alerting metrics, it can automatically redeploy the frame jobs that might require manual operation in the past. And also for the optimization of frame, like I mentioned before, then we can also define a rules to auto rolling this upgrade to the running job based on the metrics. And we can also leverage this Autopilot to implement our own resources auto-scaling. As you may know, Frame community also offer a open source Frame auto-scaler, but we still choose to implement our own for several reasons. First is our Autopilot, we can define the operational window to ensure the best stability. Also, we can prioritize what tasks to be scaled, like the old low priority tasks. And our auto-scaling can compatible to any version of Frame, because especially the Frame version with lower than 1.18, which is doesn't supported by the open source Frame auto-scaler. And last but not least, our Autopilot is have a better extendability that we can just simply add more metrics for the scaling decision. Even we can fit the Frame auto-scaler metrics report to gain the faster auto-scaling capability. After we apply the auto-scaling rule to our cluster, the overall usage actually reduced. But we still cannot reduce the machines we use. Why? It is because the default Kubernetes scheduler will try to deploy your pods in a even manner to ensure the overall cluster usage are evenly used. So, but this leads to resources fragmentation. After some research, we found that the bin packing scheduling strategy might help with this situation. From the graph on the left, it is the default behavior of the Kubernetes scheduler with the least request policy. And from the graph on the right, the bin packing policy can help us to redeploy the pods to the nodes with more to a higher utilization to ensure the low resources fragmentation. After we apply this strategy, we still cannot scale in our machine. That's why let me invite my colleague Jenny to share how we found the final piece of puzzle in order to actually reduce the number of machines.
We basically use cluster autoscaler, a Kubernetes tool, to help scale in and up our machines on our Kubernetes cluster. So there are several reasons why we still can't scale in our machines. The first reason is not all of our pods have the potential to be scaled down. And still there are some pods existing on our nodes, under a low utilization node. So the utilization of these nodes still does not meet the scaling down requirement of the cluster autoscaler. And secondly, the replica set of the task manager is 0. And this is not safe to evict by the cluster autoscaler. So we need a descheduler to safely evict the pods from the low utilization nodes from our machines. So basically, the workflow of our descheduler is like this. Firstly, it will check if the cluster has met the scaling down criteria. For example, if it's after 8 p.m. and if the cluster usage is under 90%. And secondly, it selects the nodes with low utilization. And then it marks the node as unready, unschedulable, so that when we evict the pod, there will be no pods rescheduled to the nodes. Then we evict the pods from the nodes. And then if the task manager has been evicted from the nodes, the job manager will discover and then restore the task from the last successful checkpoint, so it's safe for us. Then the descheduler will keep monitoring the nodes and the cluster and send notification when the node has been scaled down by the descheduler and the cluster autoscaler. And thanks to the work we have done before, as we have mentioned, we have achieved a lot. And firstly, our 100% of task has been migrated to our new cluster successfully and without much manual work. And secondly, more than 15% of our machines has been scaled in during non-peak hours. And thirdly, our whole platform has been more stable than before, and we don't need much manual maintenance. And next, I will introduce how we begin our journey towards Paimon. Firstly, this is our data warehouse infrastructure in Lalamove. From the bottom to the top, you will see there are several layers. And the ODS layer is consuming the database changes from tables like order attribute, order event, and the second layer, which is detail layer, is consuming the change from the ODS layer and then joining the changes from the ODS layer. And the DWB layer, which is the base layer, is built upon the detail layer. And the data mark layer is producing the matrix to MySQL, HBase, Doris, and other data applications. And a typical scenario in our data warehouse is something like this. Firstly, there are two tables like order and order freight, which is producing database change, bin log change as a stream to the downstream. And we need to do it in a streaming join. We need to join it together in a streaming manner. And secondly, there is a table called order attribute, which is the key value table. It needs to be synced into HBase. And subsequently, we need a task to join them together by a lookup join. And then to reach our detail layer. So as you have noticed, we have two kinds of join here, streaming join and lookup join. And join has brought out a lot of challenge for us. Firstly, we have to introduce in-memory cache for our lookup join to reduce the frequently assessment to the HBase. But another streaming job is syncing into the HBase, which means that the in-memory cache is not always synchronized with our HBase. So it brings the inconsistency and latency. And secondly, the streaming join has some issue. Streaming join has to keep this state in the memory for both tables. So if you are joining two tables, then Flink will keep this the intermediate result in the state in the memory. So as time goes, the state will be booming, and it's and it's resource consuming in this case. And what's worse, our upstream application architecture upgrades and introduce even more tables. And we all need to join them together to build our detail layer. So it has made our data pipeline more and more complex. And so, we have to start to explore new options. And this is why we chose Paimon. Firstly, it supports flexible merge functions like partially update, which we can replacing join as partially update to simplify our data pipeline. Secondly, it supports reading and writing in both batch and streaming. Thirdly, it provides a change log producer, and it allows us to perform computations on an incremental updated data set, which has reduced our computation cost. So how we resolve the join problem? We resolve it by replacing join with a partially update. So you can see we created a table with a primary key as order ID. And the several tables will partially update the column they produced. And then every stream, once updated, they will output the downstream in stream. So there won't be much data inconsistency and latency. And we could also utilizing the LSM data structure and compaction to merge and produce change log to the downstream. And to ensure the data, to ensure stability, we take several steps to migrate from our current data warehouse infrastructure to the data lake infrastructure. Firstly, we just replacing the detail layer from Kafka to Paimon. And then several tables from the ODS partially updated to the table in our DWD layer. And then another task is consuming from the detail layer, DWD Paimon table, and get the change log and produces to a Kafka. And our downstream layers are still querying from Kafka. This reduced the cost of migration. And the second step is to migrating all of our layers, including detail layer and a base layer, to Paimon. And by doing this, we can do both batch processing and streaming to our DWB layer and DWD layer. And as we know, Kafka is hard to query the historical data and hard to query. So we can leverage Paimon for us to do time travel. And we intended to provide the stability and observability for using Paimon. Firstly, we provided observability like we are using Kafka. We are monitoring consumption lag and checkpoint stats so that to make sure our jobs are running safely and smoothly. Secondly, we use data lake management tool named Amaro to help us to visualizing the files and check if there's some small files problems. And Paimon has provided many system tables for us to extract metadata about timestamp, snapshots, tag and branch, and including consumer ID management and lifecycle management. So, and this is just our first step towards our data lake, and I think we will achieve more in the future. So let's see our future roadmap. Firstly, in the cloud native side, we will explore more scheduler framework, like leveraging Unicorn or Volcano to utilize more scheduler strategy. Secondly, we'll leverage large language models to help us to identify the problems in our maintenance, such as, for example, when users don't have much deep knowledge of Flink, we can identify the root cause for them and then explaining to them the issue, and then advise give them suggestion on how to tune the task. And about the data lake side, we will explore more functionalities in Paimon, including merge functions like aggregations and indexes, so that we can use Paimon in more scenarios. And last but not least, we would like to unify our batch and stream processing so that we can reduce our development cost and computation cost. And that's all for us sharing. Thank you.
Thank you.
Thank you so much for Mr. Owen and also Ms. Jenny. Thank you so much for the very insightful and also enlightening presentation.